I think all of you could have fit in there last year. Oh, no. Anyway, open ARM GPU drivers. A lot of stuff happened in the last year. It's been an amazing year. So we all know the problem we have right now is that we have an enormous amount of devices out there who are running Linux. All those Android devices, they're running a basic Linux, and what we're mostly lacking to run our own full GNU Linux on it, or any other like cyanogen mod, is the user space binary drivers. Better now? Okay. Hopefully a bit more stable. No? No? Oh, well. Notes. One of the problems that we have is that these devices are fully treated as embedded devices. So the vendors and usually SoC makers are even worse at that, especially the Chinese ones. They bring up one chip, throw out the code, never think about what happens with it afterwards, and then get on to the next chip. This then goes down to the device vendors who do the same thing, bring up their own device, add touch panel, add battery and this and that, and then throw out the device, and they never ever pass anything on. Sadly, they often still violate the GPL, but we're gradually getting there and convincing them that they have to at least commit to this license and keep it in action. One thing that this never ever will solve by its own, the license thing will never ever solve our GPU binary drivers. That's in user space. There is no obligation for the vendors to free that for us. We just have to go with whatever we can get at this point. Another option we can do there is go and talk to the vendors themselves, but they at this point see little to no benefit of open sourcing, or either open sourcing their existing software or providing us documentation and let us write, or even sponsor us to write open source drivers for them. The second option is actually a lot better because it involves a lot less lawyer work. It's something we did, or I and a few guys at SUSE did for ATI. We recommended to just give us documentation, only give us documentation that you know is going to become public. Only give us documentation. You can give us early to us, but only give it to us if it's in the stage of just having to pass through the whole chain of lawyers that it has to pass through in the last checks. We only got documentation that we knew became public a month or so later. Sadly, ATI didn't always do that, and this whole story turned quite nasty a bit later. So, but that's the same story that applies for all of these vendors. You can go to them and tell them, we want open source drivers, and the first answer they will give you is, what does it bring to us? It will cost us money, but it doesn't bring us anything. You can then go and explain them these and these ways, give us documentation, sponsor these and these things, and we can get you an open driver, and you will have bigger market share and a bigger understanding from the developers. But not everybody wants to buy that yet, sadly. And this is something that we tried to do with Lima last year. We went to with Mali last year, we talked to the owners, and they were interested in listening to us. We even gave them the options, do this or do that. Do documentation, that's the easiest way, that's the quickest way to get to anything successful. And yeah, my email address wouldn't be libv@skynet.be, my community address, if that had worked out, I guess. So after the Mali thing last year, and it was a real big sense of change. We, the developers, are the only people who clearly can go and change this. We have to force a few chips open and show that this is bringing them something, that it is an advantage. We have to forcefully show it, and we have to go and sit down and do the hard work, do the reverse engineering, get the drivers out, get a user base, and at the end have those vendors' customers come and ask the vendors about supporting our reverse engineered drivers. That's the only way to currently convince these companies. And this is what we're doing. Sadly, after, that's something I'll talk about in a bit. So this talk is mostly going to focus about all the projects that have happened in the last few years, and there's 5 projects that are moving quite fast. They don't have fully working drivers yet. Some are very early in the research stage. Some have almost working drivers. And I'm going to go through each one of them and show it's this chip, it's there. The people who are doing this, some of them are in the room. I'm just going to talk about that a bit. Now, the legal angle of reverse engineering is we have a huge compatibility problem. And in the EU, I don't know what other countries, in the EU, compatibility allows you to do quite a lot. So legal, you won't run into trouble if you're using the standard reverse engineering techniques that are out there, but try to limit yourself. If you're looking into this, try to limit yourself to what you need. Try to avoid contentious paths. Try to stay away from vendor-specific optimizations in a compiler, for instance, and never ever, if you've disassembled something, never ever call that your own code, ever. That's just not free software. It's not your licensed code. So the Mali. The Mali was indeed a world beater in 2011, 2012. It's pretty much been everywhere in the last few months. It's a standard OpenGLES 1, the OpenGLES 2 chip. It has separate shaders, and I'll talk about the insanity. And Connor will talk, one of the guys reverse engineering the shaders for the Mali. We'll talk about the insanity of the vertex shader in a bit in his own talk. These SLCs have been everywhere. You have what I think 30%, no, 50% chance at least if you're buying a Chinese tablet that you're a Mali in your hands at this point. And of course, the Samsung Exynos. I know so many people who own one of the Samsung Galaxy devices. Everybody has a Mali. Now the Mali 450 is going to come out in a few months. I'm not sure how much they will push this further, but there's still some life left in the Mali family as we know it now. Mali 450 will just double the amount of fragment shaders, and it will pretty much double the performance. ARM has, in the meantime, and I was taken quite by surprise by this. I'm not sure when the Chromebook was first announced. It was October, November, something like that. And I had no idea that it was mentioned left and right, but I would have expected more noise from ARM. My guess is that the performance was not really up to it. And if you look at the benchmarks, it's not performing as well as the PowerVR SGX at this point. And the A6 in the Apple products, for instance, is outperforming it by quite a bit. So I don't think Samsung was very happy when they got the first spin of the Mali, but it will get fixed for the next generations. So Project Lima, and these are the 3 people that are driving a Project Lima. I, of course, started it, and I started working on this in FOSDEM 2011 is when the ID happened, and when we slowly moved up there and started doing the actual work. I started looking at the binary code, at a binary driver, and first thing I did was look where the shader compiler is. Is it accessible? Can we expose it separately? And then can we split this massive task up into 2 bits? Now, after FOSDEM 2012, last year, after the Mali talk here, I was put on to paid project work. And Ben was also a co-thinker at that point, still at co-think at this point. He was then off of a paid project, and he spent a lot of his time reverse engineering. That's when he started. That's when the work on the shaders started. Before that, I never ever touched shaders so far. I just used the binary compiler, still for my command stream work. Ben started reverse engineering the shaders, and all of a sudden, shortly after the announcement, shortly after the talk here at FOSDEM, Connor shows up in our channel and starts contributing. And he and Ben got kind of a good rhythm going. They were working amazingly fast. In 2 or 3 months, they had most of the basics figured out about the shaders. They have a working assembler, working disassembler at this point for the fragment shader. For the vertex shader, this chip, or is so crazy, is what Ben would say. It's impossible to have a proper disassembler for that. You have to have a partial decompiler is what was already there, but they have to go and develop a proper compiler to get all the scheduling right, to get all these details into proper code and having it useful. So Connor will talk about that in a bit. Now, when Connor first came to us, we wanted to send him a device. He was kind of reluctant to give us his address. At Linux Talk last year, I needed a photo of him. I wanted to put a photo of him up as well. And he was like, yeah, well, I'll have to ask my parents. So the only photo I got hold of is a photo of a few years ago where he built a Mindstorms robot, and this was all over the web, or at least on a few web pages. And then I looked at the age that he was then. He was 12, and this was in 2009. So Connor has been driving our project quite hard, and he's still the only guy developing the compiler at this point. And at this point, he is 16, and he is with us. Connor, could you stand up, please? So where are we with the Lima? Well, it's still research, because the way I started at it, I didn't want to be encumbered by any binary driver, by any driver infrastructure that is there, limiting us more than we need to. So I could just concentrate on getting or figuring out the chip as easily as possible without any extra. There's enough trouble there already doing this sort of stuff. At this point, we have no big secrets left in the command stream. I still need to figure out how to use multiple fragment shaders, but I'm sure it will be easy. I think I know a few ways of how to do it. Texture compression I still need to figure out, but most of the other things are a few bits left and right. Most of the other things are pretty much figured out, and I can start writing after FOSDEM, start actually looking into integrating our research driver, Limare, into Mesa and seeing what Mesa provides for us and seeing what still needs to be changed in Mesa to help us. Because Mesa currently is quite bound to Gallium, and you either use Gallium all over or you don't use it at all. And we have the standalone compiler. We want to be able to compare our own compiler against the standalone binary compiler and see where the problems are, be able to benchmark it, be able to see faults easily. So I need to go and figure out how to best fit that into Mesa. Now the compiler, Connor will talk about that in a bit in the dev room at 17:30. Scheduling is an absolute nightmare. He said yesterday that he already has 2,000 lines of code just trying to schedule the individual instructions. Apparently registers are easy to access and cheap, but the temp, and it has only a few registers, it usually has to spill over into temp registers, which are a lot less cheap, take a lot of power, and take a bit of time for results to get there, an exact number of instructions. So it is a bit crazy. This is what you get for a very good chip developed by some crazy Norwegians that was ruling the graphics world for 2 years. We have a relatively easy time getting this chip to do what we want, except for the vertex shader. Anyway, 17:30, next talk in the dev room, which is just outside here, up the stairs, and then you're in the Xorg dev room. A good thing about, and this has happened only in the last half a year, we now have full GNU Linux systems available on Mali-based SoCs. The device, I'm just showing the rotating cube a bit before, and that I will demo further on. It has a full Linux, and it is an unbelievable blessing being able to work with a full operating system instead of having to deal with Android all the time, pushing things over ADB, dealing with the NDK, dealing with all the idiosyncrasies of Bionic, having a full GNU Linux system, just being able to S-trace stuff immediately and this and that. It's pretty priceless. So the next project, Qualcomm Adreno, we all know that as the chip that is in all the Windows phones and the Snapdragons. It was the former ATI Imagion. It was sold for a measly 65 million in 2008 by AMD to Qualcomm. I don't know the exact numbers or how this would be calculated, but I think that Qualcomm is now making more per month than that off of the Imagion. Another of those really bad moves by AMD where they did the Geode a few years earlier and then the Atom happened. And now the Imagion everywhere. Anyway, now Qualcomm owns it, but before it was sold off, they apparently still sold the licenses to Freescale, so it is still available in the Freescale IMX5. Good thing about this chip is that it is unified shaders, so it simplifies the work a bit. Now, Rob Clark is with Linaro. He works for Texas Instruments at this point, and he will be joining Red Hat next week. He turned up, I think shortly after the announcements went out about Lima, he turned up into the Lima channel and was interested in doing something himself as well. So he started in, I think, April or March. He started reverse engineering the 2D engine, and in July or so, June, July, he started reverse engineering the 3D engine. Compared to us Mali people who had to do everything from scratch, he had it a bit easier in as far as this is possible with reverse engineering. This is a Radeon kind of command submission. So these things, the very high level, but actually not that hard to figure out, but it's nice to just know that it's Radeon at the top level. All these commands are known. The registers, the actual driving of the chip is something else entirely. And by July or so, Rob had his spinning blue cat showing all over. And this is around the time when he figured out that there were header files out there with a few registers defined and this and that. Anyway, Rob is making amazing progress, and he also, as a graphics driver developer for Linaro, he's doing amazing things there as well. So at one point I wondered, when does he sleep? And his answer to that was, well, there's nothing else to do in Dallas. So Rob is also sitting there. Stand up for a bit. He's made mad progress. It's insane. He's far ahead of Lima in real terms, because he went straight for a driver implementation. His driver is not perfect yet. It's still a bit slow. There's corners left and right. But he has an Exa driver there. He has a Gallium driver. Exa still needs some love, is what he's told me. Gallium, well, he can almost run Compass, and he will talk about this in our dev room at 1700, right before Connor. But he has one issue. He has no proper GNU Linux available. He still has to switch back and forth. I think he has Android in a CH root to be able to capture something from the binary driver. So not exactly the nicest situation to do reverse engineering in, but this is sadly the situation we are in. Next project is the GeForce. It's supposedly a cut on GeForce the Integra, but apparently it isn't. According to the developer, it doesn't look like any existing GeForce out there. It is a split vertex and fragment shader design, so he's in the same boat as we at Lima site, with Lima, and they're completely different architectures. Luckily, it seems a lot saner, so the vertex shader seems a lot saner from a programmer point of view, but performance may be different as well. And yes, SoCs, there's only one. There's just a Tegra. So this is Eric there. Yeah, it's the only picture I have of developers who are here who don't hold a beer. But I think he's more into meat anyway. He's looking a bit like a sous chef or a waiter, but this is not his day job. So Eric used to work for Phalanx. He was amongst the people who developed the first drivers for the Mali when it was still Phalanx in Norway. He's now no longer with ARM, and since 2 years or so he's no longer with ARM, and he joined us shortly after the announcements in our channel. And he's been watching what we've been doing with quite a lot of interest, and seeing how well this little chip is turning out and how much we actually like this chip, apart from the vertex shading being that crazy. From time to time, he couldn't hold himself and would go like, oh, I have a nice little shader here for you to look at. It might be interesting. That's the sort of thing he'd been doing in the first half year. And at one point he said, I think it was July or so, he said, let's just go and do something for myself. So he grabbed hold of, first he asked, well, can I go and look in Power VR? I have a few Power VR devices here. I managed to talk him out of that. And so we got him into the Tegra. He got himself a Tegra device. He's now using a Toshiba AC100, which almost has a free Linux. It's a bit shaky, but mostly works. And he's been, in his little spare time, he's been reverse engineering the Tegra. So where are you sitting there? There? Stand up for a bit. Why are you not wearing your hat? Sadly, though, he hasn't been able to spend that much time on the Tegra so far. But he knows how job submission works. He has shader disassemblers already for vertex and fragment shaders. And I just showed it to me 10 minutes ago as well. And it's starting to look really good already. There is a lot of command capture already, but there is no replay yet. So sadly, he won't be able to demo anything yet. And this is actually pretty bad because all these Norwegians, especially all those Phalanx guys, they're big in the demo scene, and the only guy who doesn't have a demo for us today is the demo scener. But well done anyway. This is a bit of a special case, the Vivante. So yeah, apparently it's very flexible. They are convinced that the existing Vivantes can become GLES 3 certified already, which is quite interesting. I wonder if there is any microcode going in there. I don't think so. The developer says no microcode. It just works like that. It's unified shader design. So you only have to reverse engineer one shader processor, which is nice. And it's available in of course, the IMX6, which will be kind of big this year, I think. And of course, a lot of other Chinese vendors, even the Ingenic and long soon they're MIPS based. So even MIPS has a chance again with good 3D. Now, Vladimir Wumpus turned up back in October, and I was being fed a few very interesting patches. To be able to, one really cool one was where my first bring up of Mali was under Android. So I had to provide people a way to compile their existing Lima driver or Lima research driver or a standalone compiler against the libraries from Android, the actual user space. And therefore we had scripts and this and that to pull in all the libraries to make sure that this whole dependency tree comes in. Wumpus came around and he said, why are you dealing with that? Just create a fake binary with that symbol in it. And there was a few more things where he's a really, really cool guy. He got us all the render state, like things like blend modes and depth settings and this and that. He got through that in the wiki. But this was at a point where I was still cleaning up, where I finally got some time, where I was still cleaning up my Linux tag code. So I had all these things that I had already done, but it was in such a nasty bundle together. I was cleaning it up. I couldn't give him that yet because it wouldn't help him that much at that point. It was too nasty. And I said, wait a few weeks. Wait a few weeks. Somewhere next week is always next week in such case. Next week it will be done and you'll have it. And then he got bored of that, and then he asked, well, what can I do then? So he took the Vivante, bought himself a Rockchip based tablet, and and this is somewhere like late November, early December, and he's been making mad progress. He has full command stream capture and replay in this short a time. He is slowly prying the command stream apart, which is 1 month before the Lima talk last year. I was slowly starting to pry this apart, so this is where he is right now. And he already has a shader disassembler and assembler, so in that sense, he's already a lot further. But yeah, hopefully his shader definitely is not as insane as a vertex shader from. And this all in 10 weeks. 10 weeks with a full day job. It's amazing what he's been doing. And sadly, he couldn't make it here today, but I would like to clap for him anyway, because it's been quite amazing. Right. So the Broadcom video core. It is some SIMD DSP-like whatever, running in its own bit of ROM. About 2 megabytes of ROM is 2 megabytes of microcode it gets. It's a real-time operating system. Takes a slice of your memory. And we all know this chip has, of course, the Raspberry Pi. Now this thing is running OpenGLES, OpenVG, OpenMax, media decoding, shader compiler, mode setting, register banging. It even boots your ARM core. It is quite insane. But yeah, it's sadly what the Raspberry Pi project chose as their main SoC. Now I was asked to look into the reverse engineering this graphics driver and to at least give a quote and look at what it would take. I was asked that around Linux Tag last year. Of course, for coding for a customer. So I downloaded all this stuff and looked at it on the train. And the first thing I went and tried to find was as with Mali, was try to find the shader compiler. Can we split this task up neatly? So I fire up object dump, go into GL compile shader. Notice that it's just wrapping the original source, the shader source, wrapping something in front of that, throwing the type of shader net, throwing this into some queuing system. This queuing system then goes to the kernel, talks over some ioctls. The kernel then throws it out through some buffers to the other part, and the other part is, of course, the video core. Even the shader compiler is running on the video core. So the verdict wasn't very good, because doing this shim layer, it was like busy work. Few weeks, reverse engineering that is just throw stuff in at the top, see what falls out at the bottom. You know immediately what message belongs to what action you're doing. It's going to be pretty much GL and GL down there, just packaged differently. That's just busy work, but reverse engineering the video core, all we had was those 3 blobs that are put out for the Raspberry Pi for the different memory sizes that you allocate for the video core. And all you could immediately see is that all the addresses shifted by as much as they're from the top of memory that is given to the video core. So all you had was the differences in addresses between those 3. We didn't look any further, but the verdict wasn't good. It's its own architecture. You would have to really start from very, very far. So of course this customer wasn't taking that sort of news well, so we never got the assignment for that, which I pretty much understand. I'm not that unhappy about. But all the bigger was my surprise when in October, or was it November, the big news came out that this Broadcom video core now has 3 OpenGL drivers. And let me look through my notes. I even have a full quote here. There we go. Yeah. The Raspberry Pi is the first ARM-based multimedia SoC with fully functional vendor-provided, as opposed to partial reverse-engineered, fully open-source drivers. And Broadcom is the first vendor to open their mobile GPU drivers up in this way. We at Raspberry Pi Foundation hope to see others follow. We were sitting there in the Lima channel, all the people I just talked about, apart from Wumpus, he wasn't there yet. And we were flabbergasted. What? They were calling this a completely open stack. Why? It's just a tiny layer on top. They solve one of the biggest problems that we have with binary drivers. They solve that, yes. You can compile this and have a completely different user space. You can have another libc. You can have a different kernel. That solves a lot of things for the Raspberry Pi users. But this is not an OpenGL driver. This is not a full driver. It's running somewhere in the back. It's running in the back next to the ARM core on the video core. It is not open source at all. So we were a bit flabbergasted, amazed that they would make a brash statement like this, even though everybody else in the industry, pretty much like us, went like, what? But on the other side, it's also a bit of a stab in our direction. It was not a good feeling as somebody who, as us working so hard on getting these GPUs out and getting them free, by just doing this tiny bit of something they should have freed from the get-go, because there's nothing proprietary in there, nothing at all. We were not happy with that. So after a while, we thought, okay, in the following hours, do we respond to this? Do we let it be like it is? In the end, we decided, okay, it's too brash. I'm going to go on their forums and say, I'm sorry, this is not a proper driver. This is when things turn really ugly. Apparently, if you say anything slightly negative about Raspberry Pi, then you're the devil. And this person, Liz, I think it's wife of the, she actually supports that quite a lot. I think she's just there trying to pounce on people, trying to scare them away. I don't know. But in this case, I said, whose cell phone is that? Mine? Okay, mine. In this case, it was way too brash. And I was like, no, it's a fully open source driver. So then I went and pasted a bit of the shim layer, and then, yeah, people kind of found out that this was a lot of noise for very, very, very little. It solves a lot of problems, and if they had stuck to just this message, we have freed this shim, and it will make things a lot easier for a lot of people. Then everything would have been fine, but this statement was just too much. And the response that we had was also completely, yeah, too much. Now, when there's a lot of noise on one side, then sadly a lot of noise happens on the other side. So then came the statement of the DRM kernel maintainer, Dave Early, I'm never ever letting this into the kernel. It's not a DRM driver. They already support this architecture, so they already have the video core in the back doing all sorts of stuff that we don't know about. There is absolutely no reason to not accept this into the kernel. Clean up the code, clean up the user space, make it acceptable, get it in. It's not a DRM driver, but it is a driver that should sit under driver's GPU. There's nothing stopping that. This is how this chip is built. If you want to support it, do it properly. So yeah, Raspberry Pi, a closed platform, even though people like to convince us differently. Now, all of this happened. Let's approach this differently. After my work in May, a few days where I looked into things, and I also talked with Ben and said, what can we do here? Do you have any angle there, you as a processor developer? This or that. We might get lucky. We need time first to go and look into it deeply. Now, somewhere in July, I got contacted on IRC. And it turns out that since Raspberry Pi is such a big thing, there are so many people working on it, and some people also wanted to look into what's happening on the video core. And they had a very close look, and they found, for instance, zlib and libpng in there. And they went through a lot of patents made by Alpha Mosaic, the original owners of Video Core. They went through those patents, figured out what applies to our chip. There's even some register stuff and that in those patents. And they've been bringing together this documentation. I never heard of them since. We talked for a few days in July, and then I thought it had petered out. So this was supposed to be where my slides would have pretty much stopped talking about the video core. And then 3 days ago I went, what would have happened with those guys? And I go and look on GitHub, and I see that there's 9 people working on it still. And they're getting amazingly fast. Most of them are in Australia. Through the night I couldn't contact them. They don't work as normal open source developers yet, so they are not really used to using their own names, so I had a hard time finding out these few names already. The only guy giving me a photo is Matthias, everybody else, yeah. But 9 people are working on it, and they're doing amazing stuff. They have the scalar processor in there, fully reverse engineered, and they're now working on the vector processor in there. This documentation up there, it's quite amazing, and it has all the pictures taken out of the individual patents, reference the individual patents and this and that. They have a bin utils on there, because this is the insanity. This is the insanity of their project. They have to first support a whole new architecture. And they're just doing it. 9 people, they're just doing it. Some people are starting to look into getting a compiler started, and Matthias, the guy with the photo, actually is looking into booting. And he already has the UART going, he already has some LEDs blinking. So they are getting somewhere, and it was quite a shock of this whole talk. This was a big shock for me. I thought this had petered out. So yeah, these nine guys, please put your hands together for them, because it is really, really great. right. Okay, the power of VR. The last year or so, it looked like Mali was ruling everything. There was a few Vivantes sold. Tegra had their own SoC. Arduino had their own SoC. Mali is the one that was pushed big. Everybody is doing Mali in the meantime. What's coming up right now, now that the T604 is not as nice as they would have hoped, will be fixed in half a year or so. Now Power VR is the fastest. If you put a lot of these Power unified scalable shader engines together and burn a lot of power, I guess, and deal with the synchronization, this thing can outperform everything else at this point. It's unbelievably scalable. On the other side, with Rogue still in the pipeline, they were announcing it only at CES right now, so I think it will take half a year until it's actually in products. But the people from Imagination, they were saying, oh yeah, with our unified shader design and with our microcode that we so much depend on, we can support OpenGLES 3 quite quickly. We just provide new firmware. We need to still test some things and make sure it's fast enough. But soon we will be providing OpenGLES 3 support, which, for instance, a Mali can never do. At least not the Mali 400s and 200s. So it is a very, very flexible design, and it can be very powerful. But it is all centered around this USSE engine. This USSE engine runs a microcode that deals with synchronization and job handling. This talks to the kernel through some structs, normal C structs, which change from version to version and change with different defines or different preprocessor stuff. This microcode is fed into the USSE engine through user space, through a very awkward interface. So we have this really weird tie between the microcode provided by user space, and it's unbelievably hard to debug. Then this thing is breaking up tasks quite small, and is using a lot of sync objects to get these things working in the right order. And what I heard from a potential reverse engineer 2 weeks ago is you need at least 16 sync objects to draw one triangle. If you then know that these sync objects are just a double word allocated somewhere, allocated through the kernel, you can, if the engine complains, I'm still waiting on this sync object at this address, you never ever know unless you have everything logged up there already where it came from. It is unbelievably hard to debug. So yeah, highly adaptable, highly scalable, very versatile, currently the fastest out there. And the next Exynos, for instance, will be using an SGX, the triple core one. Next, what was the brand again? Not Rockchip. Yeah, next Rockchip. Yeah, the next Rockchip. They will not use any Mali anymore. And before that, they used, I think, Vivante. They will go for a Power VR again. So Power VR is making a few design wins at this point, but it is very fragile. It is hard to debug, and therefore hard to reverse engineer. So I work very hard in trying to keep people away from Power VR. And this is the last guy who tried it. That's quite over the top. Anyway, now the bit you're all been waiting for. Rotating things. Okay, still there. So this is pretty much where we left off last year at FOSDEM. And some of you might remember that what I was doing at the time was setting up one frame, setting up all the information for that, and then just replacing one matrix in there just to make it turn, one uniform, one matrix so that it turns. What happened after about 20 frames or so, the memory subsystem would go like, and then we got lots of geometry going bad, and you had these spots happening, and because it was clearly 16 by 16 where the geometry went bad. So in the meantime, I fixed this. It's been a year. And in the meantime, I fixed also job submission. This is not synced to the display at all. On this thing, we still need to do so much display work. The original driver is also not syncing to display. It's just, yeah. This is currently running at 477 frames per second. And no corruption. And if it's not overriding a buffer 5 times, then it looks correct. So yeah, in the meantime, I also added textures, and it's pretty clear where I'm heading with this thing. The companion cube is such a nice thing to use as a test here, because you can build up from just a standard cube, add a texture. You can go. This one runs now at 220, I believe, yeah, 220 frames per second. So it's a really nice subject to do reverse engineering with, because you can step it up quite nicely. And you've probably seen this from Linux Stack or from the videos that I put out last time. But we now have a proper companion cube with, yeah, 4,600 vertices are in that order. I got this off of Blender Swap, and it looks quite nice, this one. And this is running just barely slower. It's running at 210 frames per second. Because apparently reading a texture is the very, very expensive bit that's doing here. The other one, no textures, it was just flying. The fragment shaders were just flying. Now the fragment shader has to do the texture reads. It's not compressed yet, so we could probably save a bit there. Now where do you go from here? Well, that was still one texture, one program, one draw. Even though I was doing more draws already last year. So yeah, multiple textures, multiple programs. Yeah, one texture for the background, which is just the Milky Way, which is one program. Then you have the flat shaded cube there. Also another program. And then two of the same programs with different texture and different vertices. Now we can start looking into something slightly more interesting. This is not synced to display. You can clearly see the pattern that is used for the fragment shaders. You can clearly see this happening all the way down here. Last year I was wondering, well, I found this one pattern for scanning for the fragment shader. It might be IP related. Turned out it was something developed by a mathematician in the 1800s, Hilbert. So it's just a standard Hilbert curve. And I tested it, and yes, it's slightly faster if you use the Hilbert curve than, for instance, the curves used for textures. And then, yeah, when I said this in the channel, Connor went like, yeah, that's what I found 5 years ago as well. So yeah, there's no IP there at all. It's still using the closed source shader compiler because that teenager was not willing to give me hand-coded shaders. We are only using 2 vertex shaders and 4 fragment shaders in this. So it is actually 1 or 2 days for him, I guess, to provide me with a working vertex shader. Fragment shaders we could do already in assembler quite quickly. It's actually very simple stuff. The really special thing is I have Quake 3 Arena, which the original port was written by Oliver McFadden for the N900. I took out, because the N900, if you're with a mobile device, you have problems aiming like with a mouse and with a keyboard. So there were some cheats in there inside this implementation of Quake to make it possible to do this with a touchscreen. I removed that stuff. This thing is not playable at this point. I removed all the touchscreen stuff as well. We can probably throw in input support quite quickly, but I just haven't done it. I rigged this whole thing so that we have single frame Glass 1 dumps, and so I can have these dumps in pure C that I could use directly, and then try to replay it with Limare. So first try to port it to Glass 2 so that I would have the working shader, or the shaders that are the equivalent of what we were seeing here. Yeah, shaders up. Yeah, and so we built up Limare more and more. This is just going to run forever and ever now. It's just a bash loop. So I built up Limare more and more until we learned you have fixed all the corners and dealt with depth settings, alpha tests, and this and that. And one day I thought I had enough of these I picked a few frames left and right, about 10 all in all. I could replay them perfectly. Not completely pixel perfect, because the way we are using the vertex shaders right now leads to a slightly different calculation, and therefore leads to a few rounding errors. But that's how far it goes. It's just a few rounding errors. For everything else, we're pixel perfect. So at one point I was getting there, and I started hacking together the support for Quake 3 Arena in Limare directly, and this took about 1,100 lines. Started at around 9 in the evening, finished around 6 in the morning. Woke up my girlfriend, had supper, at breakfast. She went off to work, and I tried to run this thing. It didn't run the first go, bug left or right. Didn't run the second or third go. Fourth go, it ran pretty much until here. And then it ran into trouble because the geometry here is so complex that I needed to feed the vertex shader with a bit more memory. And I ran pretty much, where are we? Yeah, here, where the parts fly about. That's when it stopped then. I added more memory. The original driver is running this thing at 47, not this one, at just under 40 FPS, but the smaller device I was testing on was running at 47 FPS. Then the Lima version ran through at an amazing 31 FPS. This is how good the Mali is. This is really how good the Mali is. There is no secrets in there. In the meantime, this thing is running 1 FPS faster. This thing is 2% faster than the binary driver. This is really amazing because there's no secrets in the Mali. There's nothing special there. There's no strange IP there. Well, apart from, but there's nothing that you would expect on a desktop chipset where they pull all sorts of crazy things to make it go fast. Whatever optimization I've done for this applies to everything. These cubes spinning so fast, that's only after I've had this good benchmark there, after I figured out job submission. So then, we're faster than the original driver because we don't have to care about all these corner cases, all of the glass stack. We're just the research driver that just happens to look a lot like glass because that's how the hardware works, and just fits into Quake 3 Arena quite nicely. Yeah, so this is where we are at with Lima. And maybe next week, I think around now, it's time to start developing a real driver. Thank you. Any questions? Apart from being able to play it? No, not yet. I can only run this time demo. If I start the normal Quake, normally then they first have these cutscenes. They're very simple shaders, but I haven't implemented them. So that doesn't work yet. But apart from that, where? Oh, yeah?
Yeah, you mentioned that you're running regular Linux. What's the hardware that you're running it on?
Okay, so what hardware is this running on? It's an Allwinner A10.
Okay.
It's probably one of the freer SoCs out there. The vendor and most of the tablet makers are horrible GPL violators, but they were so lax with their source that it fell out at different parts. So in the meantime, it is probably one of the most free SoCs out there, and there's a really big community at linuxsunksy.org, and they've been cleaning up a lot of stuff. Hans here is doing a lot of display stuff as well. So it is really a big community, and it's going to be a big chip for us free software people, but it's not a very performant chip. This thing, if I get a Exynos, it will run 4 times as fast because it's fully limited by the fragment shader. Okay, it's too early? Too late? Okay. Yeah, okay. So, yeah, so it will be over in a bit. This is fully fragment shader based. I have a thread running, for every frame I'm running a thread. There are just 2 threads rendering for me, and just waiting on the different engines. This thing runs 30 seconds, of which 2 are on the vertex shader. It's 90-99 game, so geometry was all a bit. It was before transform and lighting was everywhere. 2 run on the shader. On the fragment shader, we run for 40 seconds of the 30 because there's 2 different threads just waiting for this to finally finish. It's just fully fragment shader limited. Thank you.